In this video, we're going to be looking at whether a sequence of numbers converges or diverges, and we're going to bring back up the concept of limits. So when we think about a sequence of numbers, the way in which we write this sequence is going to be with these terms here. So a sub 1, a sub 2, all the way up to a sub n, and it's an infinite sequence. So n essentially goes to infinity. We can also use these following notations for these sequences, so you can see like a sub n in squiggly brackets from 1 to infinity, or we also don't need to include those bounds if you just want to put the squiggly brackets. Let's look at the sequence 2, 4, 8, 16, 32, so on and so forth. So this is a sequence, and you can find the terms. And you can see here how they're named. So like the first term is 2, the second term is 4, so on and so forth. And here we want to figure out some patterns. So notice that A1 is 2 to the 1, A2 is 2 to the 2, A3 is 2 cubed, A4 is 2 to the 4th, since I'm multiplying by 2 each and every time to get the next term. And so we can find a pattern or a formula that's going to generate that sequence 2 to the n. And then that way, once we have a pattern, I can be like, okay, well then what's the 10th term? Instead of having to list them all out, I'd be like, oh, it's 2 to the 10th power. Here's a formal definition of what an infinite sequence is. Each term is each number in a sub n we call that a term of the sequence. Sometimes they do have explicit formulas that we can find. And then there's sometimes that we're looking at what's called a recurrence relation. Recurrence relations are really interesting. Fibonacci's sequence is a recurrence relation. What that is you take 1, and then the next term is 1, and then you add the 2 before it to get the next one. So, sorry if you can see my virus protection just came up. Okay, 1 and 1, so then the next term, 1 plus 1 is 2, and then you add the 2 before it. So 1 plus 2 would be 3, 2 plus 3 would be 5, 3 plus 5 would be 8. And so that's a recurrence relation because it depends on the terms kind of before it a little bit. Okay, so let's look at these examples. For each of the following sequences, find an explicit formula for each to find the nth term of the sequence. So I'm going to list out here, A1 is negative 1/2, A2 is 2/3, A3 is negative 3/4. And this way I'm going to try to figure out what a pattern would be. Well, I'm noticing that each time I'm looking at a new term in the sequence, that the number of the term number is the numerator, and then 1 more than that is always the denominator. Is that true for A4? Yes, 4 over 5. So I'm going to say that A sub n must be equal to n over n plus 1. Now what that does not account for is that I end up having this plus and minus back and forth. So I have a negative and then a positive and then a negative. So I need a way to say I have alternating signs here. The way that I do that is I say I have negative 1, and then I have 2 different options for the power here. If it's on the odds, then I want to make sure like negative 1 to the power of 1 gives me a negative, and then negative 1 to an even is where my positives are. So it would make sense that I call this negative 1 to the n. If you find that the opposite is true, okay, so all your odd terms are positive and your even terms are negative, you just do an n plus 1 or an n minus 1 as your exponent. Okay, and that's how you write that alternating term piece. All right, let's look at our next one here. So on this one, actually I'm going to change colors to purple. On this one, I have A1 is 3/4, and then I have A2 is 9/7, and I have A3 is 27/10. Now I'm noticing the top is always a multiple of 3. This is 3 to the power of 1, this is 3 to the power of 2, this is 3 to the power of 3. So I'm going to say AN must be 3 to the n. Now on the bottom, I'm noticing that I'm adding 3 each time. So this is more of like a linear term where I need A1 to be equal to 4. So if I want to figure out that pattern, one way that you could do this is you can almost treat it like you would a line. And then you want to go back to like making sure that when you plug in 1, you get 4. So that happens if I do 3n plus 1. And let's double check. Okay, so you can think of this like being like a slope of 3, rise over run. And then I want to make sure that when I plug in 1, I get 4. So 3 times 1 plus 1, yes. 3 times 2 plus 1, 7. 3 times 3 plus 1. And so that's going to be my my pattern there. All right, so we say that the sequence converges if it has a limit, okay? Also, if it's not convergent, we say it's divergent. All of the limit laws then apply as well. So let's look at whether or not these sequences converge or diverge. So if I take the limit as n goes to infinity of this term, n goes to infinity means that 3 over n is going to go to 0. And so this goes to 5, so we say that this converges. All right, let's look at this one right here. So I have the limit as n goes to infinity of 3n to the 4th minus 7n squared plus 5 over 6 minus 4 to the power of n. Here you want to use your like horizontal asymptote or end behavior laws from pre-cal to really help you. Also, if you plugged in infinity, you would get infinity over infinity, so you could use L'Hopital's rule as well. Either of those will work here. But if you look at the leading term in my numerator and my denominator, I notice they're the same degree. And so this limit is going to end up being 3 over negative 4, which means it is a convergent sequence. All right, let's look at one more here. Let's take the limit as n goes to infinity of 2 to the n over n squared. Now this is one that you could use L'Hopital's rule on. Again, you're going infinity over infinity. What we end up doing, the derivative of the top here is 2 to the n times the natural log of 2. The derivative of the bottom is 2 times n. Be careful, those do not cancel. You can continue doing this. Notice that the denominator ends up being a number eventually. The exponential function keeps being an exponential function times the natural log of the base. And so you end up getting infinity over a number. This is going to go to infinity, so this one diverges.